rotational motion. And up until now, you've looked at things that move in a straight line with constant acceleration, things that move in a straight line with varying acceleration, fireworks rockets, things like that. We've also, or with Mrs. Monroe, you've been looking at things that bounce up and down in a straight line with simple harmonic motion. That has varying acceleration and quite a complex sort of motion. There is one other type of motion which you need to be aware of because it's one of the most common types, and that is rotational motion. So give me an example, well, give me a few examples of things which move round and round in circles, which are rotational. Kiss roundabouts. Generally the high spot of the advanced higher curriculum where we all go down to Belfield Park and use the roundabouts down there for conservation of angular momentum. And we will be using fairground rides as an example because there's a lot of physics in the fairground rides. I can't actually justify the trip down to Alton Towers that some schools make south of the border, but that would be a good one. Oh, thanks, Donald. Whatever gave you that idea? Okay, so wheels. And virtually most things that actually make a car move, although a car moves in a straight line, most things to do with the car moving in a straight line actually go around in circles. Transmission shafts, wheels, bearings, all the stuff in the engine, it generally moves in circles. So all those things move in circles. So we're going to have a look at some of the circular motion on a bike. Anything else that moves that has a circular motion at home? Washing machines, yeah. Food processors, CD drives, hard disk drives, almost anything that's got a motor in it will turn things around in circles. The motor then might pull something which makes it move in a straight line. But a lot of motive power starts as moving in a circle. So actually, rotational motion and circular motion has got a lot to do with any type of motion. So we'll kick off by looking at a sort of overview of what we're going to be doing by considering our bike here. So if you, I will say again that you've got the distance that the bike travels is actually measured by the speedometer on a bike as angular displacement, and then that's converted into linear displacement. What information has anybody got one of these bike trip computers? Yeah? What have you got to program into it?
Size of the wheel.
Yeah, okay, so although the trip computer knows how many times the wheel's going around per second, you've got to program in the radius from the centre. So we'll come back to that. You've got the speed of the wheel, you've also got the distance that it travels. So these, we're going to look at the angular versions of those. Going down to the pedals and the cranks here, the force which you exert on the pedals is actually turned into what's called the torque by the force multiplied by the distance, or you might in tech studies have come across that as a moment as the thing which actually makes it move. As your bike accelerates, it accelerates linearly, but there's also an angular acceleration, that the wheels themselves start at rest and achieve a much bigger and bigger angular velocity, so there is angular acceleration there. How a bike wheel is designed to improve that angular acceleration? Has the thing got angular momentum as well as linear momentum? Like again, how a bike's designed to try and improve the angular momentum of the bike as opposed to just the linear momentum. All these things can save a bike rider effort and energy if they're designed right. There's also, just turn around a second, on the gearing system on a bike, that's using torques and moments, and we'll come back to all of that because that's the thing that actually makes the bike move and makes the wheels turn in the first place. So a lot of what we've dealt with in linear motion actually has a correlation with rotational or angular motion. So we're going to kick off with a couple of basics, and I'd like you to be able to, by the end of this morning, be able to measure the angular velocity of a bike wheel, and there is a way to do that. But we first of all need to think about angle. Okay, so zip back. A wheel or a bike wheel is moving from there to there. It describes an angle, theta. What units do we use for angle? Sorry, Donald? So you're giving this plea for degrees. You're in the campaign for real angle, and you want to use degrees. Why degrees? Why are degrees such a good thing? It's easy, okay. Because you know that in a full circle, you've got 360 degrees. Why 360, do you think, in the past, when they were divvying up the compass points? It's related to the number of days, yes? And it's also a nice number that it's easy to divide. You can divide it by 3, you can divide it by 4, you can divide it by 12. So it was easy to divide up the compass points into whole numbers of degrees. So that made it quite straightforward there. The other thing is that degrees are a completely man-made phenomenon. Somebody years ago just said, right, there's 360 degrees in one full circle, and that's it, end of story. Nature and maths does not agree. Because if you differentiate or integrate an angle in degrees, it just doesn't work. It's not a pure number. So that brings us back to the other unmentionable measure of angle, units of angle, which you don't like because you don't really use them that much. Which is, Alistair? Yeah. So, like it or not, for advanced higher, as soon as we start measuring angle, we've got to use radian measure. Roughly, just try it there. Going from there out to sort of there, how much is 1 radian? Just less than 60 degrees, 1 radian. So that's 1 radian worth of measure. And a screwy kind of number, but why is it such a sort of imprecise number of degrees? What is the definition of 1 radian? Oh? It is. If you go all the way around what we would call 180 degrees from one side to the other, half a revolution is pi radians. But what is the definition of 1 radian of angle? Tom?
Where the length of the arc of the circle is the same.
Okay, so you take the angle from there. If that's your radius, if you measure the arc, and that's also the radius, then that would be 1 radian of measure there. So to get any angle in radians, say if you've got a radius here, and you're trying to find out what that angle would be, you'd need to measure that length there. So theta will be equal to the length divided by the radius. And it's in radians, and because you're dividing length by length, really the dimensions or the units for radians, there are none. So that's first thing. Theta, the angle, is just the length divided by the radius. Now the next bit is how do we get the angular velocity? If that's our angle, that's really our angular displacement. If a wheel turns around by so many radians, that's the displacement that it's covered in terms of angle. So to get the angular velocity, what would you do with angle to give you angular velocity? Just as a reminder, if you had displacement as the linear length and you wanted the velocity, how would you get velocity from displacement? Again, we're thinking in terms of advanced higher now. Stars, what would you do with displacement to get to velocity for any kind of motion? You differentiate it, so you get ds by dt. So to get to angular velocity, from the angular displacement, how would you get that? Anna? Differentiate it. So angular velocity omega is d theta by dt. And the units for angular velocity, the number of radians that this is going to cover per second, you're going to get radians per second, okay? So rad seconds to the -1, that's your angular velocity and the units. That's what we're after this morning. Can we actually get a measure for the angular velocity of a wheel or a turntable? What's going to be the easiest way to do that? Well, think back to linear motion. If you wanted to get the instantaneous speed of an object, how would you have done that, even at standard grade? You'd use a light gate. You'd have a card or the vehicle passing through a light gate, and you'd be able to work out the instantaneous velocity from that. Now, how are you going to get angular velocity for a spinning bike wheel? I'll leave you to think about that, and then we'll get it set up.